Assalamualaikum and good evening. I bid to the respectful examiners. My name is Anisuraya binti Amakhar alias Amakhar, and today I'm going to present a review video based on my thesis entitled Mixed Class Former Effect of Potassium Borotellurite Classes on Optical Properties. So these are the outlines highlighted in this video. Glass is a material with a distinct structure and can be classified as network former, intermediate, or network modifier. Examples of applications of glasses used in science industry are optical fiber technology, solar cells, and optical waveguides. Next, mixed class former effect, or known as MGFE, occurs when combining two or more network formers such as boron trioxides B2O3 and tellurium dioxide TeO2, which contributes to borotellurite classes. Meanwhile, for the doped glass, dopant elements are added to a chemical substance to change its optical properties. So, there are two contradictory results that I have found from the previously conducted research. According to Elkoskani et al. In 2019, the findings revealed that the bandgap values increased as the quantity of TeO2 in the glass system increased. This was due to the formation of TeOB bridge structures that will alternatively decrease the quantity of NBOs. In contrast, another study by Kaki et al. In 2019 on glass system with stated composition showed that the optical bandgap values decreased with increasing of TeO2 due to an increase of non-bridging oxygen formation within the glass system. Thus, it proves that the addition of different mole percents of TeO2 contents and feeds doping with different elements leads to different visible changes in optical properties of the gases. The objectives of this research are to prepare stated classes system using melt quenching method with X equals to 0 until 0.4 mole% and to investigate the effect of borotellurite radiation on optical properties of the stated class system using UV spectroscopy measurement. Research on the optical properties of the borotellurite classes has been the subject of many prior studies, for instance, SRD analysis. It is used to determine the amorphous or crystalline state of the materials. As evidences in 2017, Lakshminarayana et al. Had conducted a study on zinc molybdenum borotellurite classes and found that the absence of distinct peaks and reflections in the SRD patterns demonstrates that the produced materials have an amorphous structure. A single broad harm observed in the range 2 theta equals to 20 to 35 angles represents the glass structure's intermediate range order. Another study conducted by Samsudin et al. In 2021 revealed that the broad harm in the spectrum occurred at around 20 to 30 degree angles, and these corresponding to the non-crystallizing mid-range structure. The absence of well-defined peaks showing that the short-range atomic arrangement and the lack of crystalline phase indicate the sample's amorphous nature. Next, FTIR spectroscopic measurements were conducted to gain insight on the critical structural unit behavior and arrangement in the examined glass. As evidences, Elazomi et al. Had conducted a research in 2018, and the results showed that the stretching vibration of the TeO2 in the TeO4 and TeO3 was represented by the absorption band between 600 until 700 cm. Next, in 2016, Sabri et al. Had identified the BO4 and BO3 vibrations group. The absorption bands from 815 to 1120 cm were attributed to stretching vibrations of BO bonds in BO4 unit into 3 tetra and pentaborate groups. In addition, study of the optical absorption age provides information on the optically induced transitions and optical band gaps of materials. A research of optical band gap that vary with B2O3 content was studied by Elkoskani et al. In 2019. The results show that band gap values increased with increasing amounts of B2O3 in the glass system up to 30 mole%. Thus, quantity of NBOs formation decreased with the addition of B2O3 to the glass system. Next, according to a previous study on tellurite glass doped with PBO by Elazomi et al. In 2018, the refractive index increased with increasing of ZNO content due to the replacement of TeO4 plus and Pb2 plus with less polarizable Zn2 plus ions. In addition, another study by Al-Hosqani et al. In 2019 revealed that B2O3 addition in the class system caused an initial decrease in refractive index from S equals to 0 mole% up to 20 mole%. The chemicals and instruments used in this experiment are listed as follows. For the sample preparations, first of all, the stoichiometry ratio of each chemical powder was calculated and weighed using an analytical balance. Then the chemical powder was mixed in a milling machine for about 1 hour. The mixture was placed in a ceramic crucible and melted in the box furnace at a temperature of 1100 degrees Celsius for 1 hour, and then the molten glass was quenched at 350 degrees Celsius in stainless steel mold for another 2.5 hours. And finally, the sample was characterized using SRD, FTIR, and UVV spectroscopy measurements to determine the structural and optical properties of the glass. Moving on to the results and discussions of the experiment. Now, as you can see, figure 4.1 depicts the SRD patterns of the stated glass system, and there are no distinct or continuous sharp peaks in samples at X equals to 0 until 0.3 mole%, demonstrated that the samples are amorphous. However, at X equals to 0.4 mole%, the glass sample exhibited partial crystallinity in an amorphous matrix. The partial crystalline peak at 25.79, which is denoted as A, may be caused by the alpha TeO2 phase. Meanwhile, the peaks at 29.31, denoted as B, and 31.95, denoted as C, are results of the presence of the gamma TeO2 phase. Another partial crystalline peak occurred at 12.8 in the same sample denoted by star, but these have been identified as the unknown phase. Next, figure 4.2 illustrates the IR absorption spectra for a composition of glass samples. The absorption bands are mainly observed in 3 regions in FTIR spectra for borate classes with varying numbers of 600 until 800 cm, 800 until 1186 cm, and 1150 until 1550 cm. And the spectral bands depicted the vibration mode for telluride and borate structural units. From this assignment list of IR spectra, we can conclude that the spectral range of 521 until 653 were due to symmetrical striking vibrations of TeO4, and 764 until 788 were due to stretching vibrations of the TeO2 group. Meanwhile, the band ranged from 876 until 1186 cm were attributed to the BO4, while bands from 1207 until 1491 cm were represented by BO3. Figure 13 illustrates the variation of N4 for the glass sample, and the value of N4 reached a minimum at X equals to 0.1 mole% with the addition of TeO2. The rate of BO formation is correlated with the concentration of BO4. Thus, lower values of N4 indicate lower BO formation. Next, to evaluate the type of transition for optical bandgap, the experimental E-opt values from the extinction coefficient were compared with the E-opt values calculated from the Moore-Davis model using different N values. Thus, from Table 2, we can conclude that the E-opt values for N equals to 3/2, which is the direct forbidden transition, were in correlation with the E-opt values calculated from the extinction coefficient method. From figure 16, we can see that the plots of N and the optical bandgap exhibits contradicting trends. The E-opt values dropped at X equals to 0.1 mole% and then increased at X larger than 0.1 mole%, shows that the variation of E-opt correlates with the trend of N4. In conclusion, the amorphous nature of the glass samples from 0 to 0.3 mole% were confirmed by the SRD data. Then IR absorption peaks indicated the existence of BO3 trigonal, BO4 tetrahedral, TeO3 and TO4 units. Meanwhile, for the optical bandgap, initial drop in E-opt and increase in N at X equals to 0.1 mole% could be due to NBO formation from BO3 units, whilst increase in E-opt at X larger than 0.1 mole% is due to the BO4 formation in the glass network with TeO2 addition.